I'm Norman Wappinger. Today we're going to look at null points and null lines in universal hyperbolic geometry. So this is a new approach to hyperbolic geometry in which the points that are usually called at infinity are actually playing a very central and crucial role. We're calling them null points, and the associated dual lines are called null lines. So here's our official definition of what these things are. I remind you about duality, that if you have a point, which in our context is just a proportion of three rational numbers enclosed in square brackets, then its dual is a line, which is a proportion of three rational numbers enclosed in round brackets. And this dual operation simply changes the square brackets to the round brackets, or if we went the other way, changing round brackets for a line to square brackets for a point. So now we can say that the point A, given by the proportion x to y to z, is null precisely when A is incident with its dual A perp. In other words, when A lies on the dual line. So when would a point like this lie on its dual line? Well, the incidence is exactly x times x plus y times y minus z times z equals 0. So here is the crucial relation between x, y, and z that determines a null point. And dually, a line capital L, say little l to m to n, is a null line precisely when L is incident with its dual point. In other words, when L passes through the dual point. And that occurs exactly in the same way, precisely when L squared plus m squared minus n squared equals 0. Now it's obvious, let's just point it out, that if A is a null point, then its dual, A perp, is a null line, and conversely. So here's an example of a null point. The point 3, 4, 5. That's null because 3 squared plus 4 squared minus 5 squared equals 0. And I remind you that point in the plane, we would picture it as the point with usual xy coordinates 3 over 5, 4 over 5, which we do recognize as a point on the unit circle. So that's the geometrical meaning of a null point. It means we're on our basic unit circle. And here is an example of a null line, because 5 squared plus 12 squared equals 13 squared. So 5 squared plus 12 squared minus 13 squared is 0. That's 25, 144, 169. And that is geometrically the line with equation 5x plus 12y equals 13. And if you graph that, you would see that it's actually a line which is tangent to the unit circle. And in fact, it's tangent to the unit circle at the point 5, 12, 13 in square brackets. In other words, the point 5 over 13, comma, 12 over 13 in usual x and y coordinates. So the null points and null lines play a central role in the subject. In classical hyperbolic geometry, what we are calling null points are called points at infinity. They are technically speaking not actually part of the geometry, but rather out at infinity somewhere. And what we're calling null lines are essentially invisible or non-existent in classical hyperbolic geometry. But for us, these are the distinguished objects in our theory. They have a sort of elevated role or higher status than any other points and lines. We're going to treat them always a little bit differently with special respect. It turns out that null points and null lines are mathematical equivalents of photons in physics. So a photon is a particle that essentially gives us light, and it travels at the speed of light, and it has 0 mass. So it's kind of free from the constraints of these other grubby particles like electrons, protons, neutrons that make up ordinary matter. Photons have a distinguished role in physics. They are the carriers of the electromagnetic force, and they are sort of central in Einstein's theory of relativity. And we're going to see that those photons and these null points and null lines are very analogous, and the mathematical connection is actually quite deep. All right, I want to go back now to a topic that we treated in one of our earlier videos, the rational parametrization of the unit circle. The unit circle, x squared plus y squared equals 1, we also call that the null circle, because the points that lie on it are exactly the null points. Now I remind you that we had a parametrization of the points on this circle. They were all of this form: 1 minus t squared over 1 plus t squared, comma 2t over 1 plus t squared. And we denoted that by e of t. And the geometrical significance of t was that it was the coordinate on the y-axis, such that when you join this point with that point on the y-axis, where that line meets the circle in the second place, that's e of t. So in this example here, if t is, say, roughly a half, then this would be the point e of a half. And there was a bit of an exception in that picture. We had to treat this particular point in a rather special way. So there's no value of t that gives this point here. It's a bit of an exception. So minus 1, 0, however, can be sort of vaguely thought of as being e of infinity. It's what you get when t approaches infinity, all the way up there. Then the line, the green line, would be actually vertical. So this is a very important parametrization. I've emphasized how important it is. It's far superior to the usual cosine-sine parametrization, for example. But now we are in a position to go further, to actually improve on this important parametrization. And we're going to improve on it by incorporating this special point in a framework that's the same as all the other points. So we're going to remove this slight hiccup that we have one exceptional point. And the idea is that we're going to move from a rational parametrization to a projective parametrization. It's a rather useful and elegant extension. So let me just remind you about our projective line. So we're thinking about the projective line. Well, it's things like this. It's a proportion t to u. And geometrically, it is representing a line through the origin in a two-dimensional affine space. And I remind you that a line through the origin, most of them, intersect this reference line when y equals 1, this green line here, in a point. And you can get that point by scaling. So if we're looking at a line through the point t comma u, then if we divided both of these by u, we would get t over u1. That would be actually a point on this line here. So in terms of the proportion, t to u is the same as the proportion t over u to 1. That, however, only makes sense if u is not equal to 0. If u equals 0, it means we're talking about a line in this horizontal direction which doesn't intersect or meet our reference line. Such a line is parametrized by the pair 1 to 0. So the point about the projective line is that it's essentially an affine line plus one extra point. It's parametrized by a rational number, parametrizing a point on this reference line, together with one more point, which is this particular combination, 1 to 0, which in some sense is playing the role of the point at infinity on this reference line. If you move out in that direction there, further and further and further out, then the corresponding line through the origin approaches the horizontal, that particular value there. So the projective line gives us an extension of the rational numbers by one more point. And that's exactly what we need in order to parametrize this circle, because we needed rational parametrization plus one more point. So the idea is that we should parameterize this unit circle not with a rational line, but actually with a projective line. So let's see how that works. Here is the projective parameterization of the unit circle, which describes all the null points. All of them now. Every null point alpha is of the form alpha equals e of t to u. This is a new object. What's inside here is a proportion of rational numbers. By definition, this means this triple. U squared minus t squared, this squared minus this squared, to 2ut, twice the product, to u squared plus t squared, u squared plus t squared. All enclosed in square brackets, so it is really a point. And the claim is that every null point is of this form for some unique proportion t to u. First, let's observe that this squared plus this squared really is this squared. That identity is the basic identity underlying Pythagorean triples, going back to Euclid in the ancient Greeks. So this is definitely a null point. The other thing to observe is that if we consider the proportion t to 1, in other words, when u is equal to 1, we get 1 minus t squared here, we get 2t here, and we get 1 plus t squared there. And then 1 plus t squared is never 0, so if we divide by that, we get 1 minus t squared over 1 plus t squared, comma, 2t over 1 plus t squared. So we're recovering the earlier rational parameterization in terms of what we called e of t. But the advantage now is that when we consider the proportion 1 to 0, which is different from this because now the second component is actually 0, we plug that in here, we get 0 squared minus 1 squared, that's minus 1. 2 times 0 times 1, that's 0. And 0 squared plus 1 squared, that's 1. So we're getting minus 1 to 0 to 1, which is the point minus 1, 0 in xy coordinates. So we're recovering the rational parameterization with proportions of this form, and we're recovering that extra point that used to be anomalous with this proportion. But now we don't have to worry anymore about this special case. When we just look at this formula here, any two rational numbers there, as long as they're both not 0, we're going to get a null point, and all null points are of that form. Okay, there's exactly a dual statement in terms of null lines. So every null line, say phi, is of the form phi equals capital E of t to u. Has exactly the same form, but capital E referring to a line, because lines are capitals. And it's in round brackets telling us, yes, it is really a line for some unique proportion t to u. This parameterization of the unit circle, which is essentially what we're doing here, is lovely. The first chapter in algebraic geometry texts ought to have this formula in it, because that's a crucial and important thing that algebraic geometry tries to do, is to try to parameterize curves. The unit circle is the simplest curve, other than a line. There's the projective parameterization of it. It's also a very useful formula in practice. If you're doing just work in the plane, it's a lot easier to think in terms of homogeneous coordinates and proportions of 3 rational numbers or 3 integers than often working with x and y coordinates with fractions. So it's of great practical utility, but it's also of importance theoretically, as we'll see. We'll see repeatedly the importance of this parameterization. Let me at this point make a few remarks just to connect this parameterization with some basic linear algebra. These 3 algebraic objects that are occurring in the 3 positions in that formula are what are called quadratic forms in algebra. So if you think about a point, or perhaps a vector in space with x and y coordinates u and t, then this function of u and t equals u squared minus t squared is a quadratic form. It's really giving a kind of quadrants and determines a geometry in the two-dimensional affine space. The R here stands for red because exactly these three quadratic forms, the red one, the green one, and the blue one, are the basis for chromogeometry, a new development in planar affine geometry, which is described in my YouTube series Wild Trig 53 to 57. This quadratic form here is the usual one associated with Euclidean geometry. These two quadratic forms are hyperbolic versions of them, closely related to Einstein's special theory of relativity, as described by Minkowski. They're sort of two-dimensional versions of that. And it turns out that these three quadratic forms fit together in a beautiful, lovely way. So the three coordinates that are appearing in our parameterization of the unit circle result are actually also the same as these three fundamental quadratic forms. And I point out once again that this whole projective approach via homogeneous coordinates really establishes hyperbolic geometry as a theory over the integers. The rational numbers can be finessed by using that third coordinate in our proportions for the denominators to go. So we can always clear denominators by using that third coordinate so that the three elements are actually integers. And then another point is that these three quadratic forms also have associated to them things called bilinear forms. Now you don't really need to know this, I'm just pointing this out for those of you who have had a little bit of algebra, linear algebra. So the corresponding bilinear form to this one here is a function of two vectors. So if you have two vectors u1 t1 and u2 t2, then you can combine them with a sort of a dot product by this formula here, u1 u2 minus t1 t2. And then if these two vectors happen to agree, then you recover the quadratic form. Similarly, there's a green bilinear form given by t1u2 plus t2u1, and if these vectors are the same, then you recover the green quadratic form. And the blue one is just like the red one, except that there's a plus sign there instead of a minus sign. So in linear algebra, whether you're working with a quadratic form or whether you're working with a bilinear form, they are very closely connected. But we're going to see now that this bilinear form also occurs in our context here. Now that we know how to parameterize null points, we want to describe lines that join two given null points. So this is a generalization of an earlier result that we talked about, where we've already talked about the line through two null points. This is now a more advanced and more general theorem, a better theorem. We'll call it the join of null points theorem. It says that the line L passing through the two null points alpha 1, which is e of t1 to u1, and alpha 2, which is e of t2 to u2, is this one right here. It's a line, and its three entries are u1 u2 minus t1 t2, t1 u2 plus t2 u1, and u1 u2 plus t1 t2. So these are exactly the three bilinear forms that I mentioned in the previous slide. That's the red one, that's the green one, that's the blue one. I'm going to give two proofs of this important result. All right, so the first one is, let's just take this formula and check to see that it works. The first thing that we really ought to do is to check that this is in fact a valid proportion. What does that mean? Well, if you just write down an arbitrary proportion, you really ought to check that all three of those entries are not zero. Right? I remind you that a proportion like this, the entries can be completely arbitrary, but they are not allowed to all be zero. So let's check that in this case, these three cannot all be zero. Suppose that they were all zero. suppose that this was equal to 0, that this was equal to 0, and that this was equal to 0. Then if we take the first expression and the second expression and we add them, then we find that u1 times u2 is 0. And if we take the difference, we find that t1 times t2 is 0. But we know that t1 to u1 and t2 to u2 are both valid proportions because they're coming from these 2 points. So in other words, these are not both 0 and these are not both 0. So in this expression here, one of these two is 0. If this u1 is 0, then, because this is a valid proportion, t of 1 cannot be 0. So t2 must be 0. In which case, u2 and t1 are not 0. Because if u1 is 0, then t1 can't be 0 because this is a valid proportion. And if t2 is 0, then u2 cannot be 0 because this is a valid proportion. So that's one possibility. The other possibility is that u2 is 0. If u2 is 0, then t2 cannot be 0, so t1 must be 0. And then it must also follow that u1 is not 0 and t2 is not 0. So either this combination holds or this combination holds. But then in either case, if we look at this middle term, which we haven't considered yet, t1 u2 plus t2 u1, in this case here, the u1 t2, that term would be 0, but this one here is the product of two non-zero things. It would definitely be non-zero. And similarly over here, if this was happening, then u2 t1, these would be 0, but these would both be non-zero, so this whole combination would be non-zero. So either way, the middle thing is not equal to 0, which contradicts our assumption that they were all three 0. So we've just established that, yes, this is actually an honest expression. Those three numbers can never be all 0. Now the other thing that we have to observe is that the 2 points that we started with actually lie on this line. How do we check that? Well, e of t1 u1 has coordinates u1 squared minus t1 squared, 2u1 t1, and u1 squared plus t1 squared. So we need to check that this times this plus this times this minus this times this equals 0. And that is an identity. Just expand it out and you will see that all the things cancel. You do in fact get 0. So alpha 1 necessarily lies on L. And the argument is symmetric. Exactly the same thing holds for alpha 2. So this expression has the property that both these points lie on it. So if those points are distinct, then this is indeed the line passing through those two null points. So here's a second proof of this result. Let's start with the two null points. Here is e of t1 u1. We'll call that alpha 1. Here is e of t2 u2. We'll call that alpha 2. And let's just compute the line joining those 2 points. So we'll assume those 2 points are different, because they have to be different in order for a line to be determined by them. So suppose they're different. Let's calculate the line through those 2 points by using the j function. How does that work? Well, we have 3 components. The first one is this times this minus this times this, or this times this. There it is there. That was a 2 by 2 determinant. The second component is another 2 by 2 determinant. It's this times this minus this times this. And the third component is another 2 by 2 determinant. It's not this times this minus this times this as you might think. It's negative of that. It's this times this minus this times this. So if you expand all these 3 out, you'll see there's a common factor of 2. So after we divide by that common factor of 2, then we notice that each one of them actually factors. The first one as t1 u2 minus t2 u1 times u1 u2 minus t1 t2. The second one as t1 u2 minus t2 u1 times T1U2 plus T2U1. And the third, T1U2 minus T2U1 times U1U2 plus T1T2. So please check that. There's a common factor. We can divide by that common factor because we're just talking about a proportion. And because we know that common factor is not equal to 0. How do we know that? Well, what would it mean for this to be 0? It would mean exactly that this proportion is equal to that proportion. That's exactly when this proportion is equal to that proportion, the condition T1U2 equals T2U1, or this thing equals 0. So after we cancel that common factor, we just get the three bilinear forms that we're interested in. That's our formula for the line through those 2 points. Now there's something interesting here to remark. We shouldn't be surprised that this common factor is occurring. In fact, after you've been playing around with this subject for a while, you come to expect this kind of thing. Why is that? Because the algebra does not know whether this input and this input are actually the same proportion. If T1U1 and T2U2 were the same proportion, then how can we possibly get an equation of a line out of this? There is no single line through two identical points. So something must break down when the 2 points are identical. And what breaks down, the only thing that can break down is that the expression for being identical appears as a factor of the 3 coefficients here. So that if the 2 points are in fact identical, we're going to get 0 to 0 to 0. So after a while you could anticipate the existence of such a factor when you write down something like this. You know it's got to be there, or at least you feel that it's got to be there. So you can look for it and find it. Okay, so this very fundamental formula, okay, formula for the line joining 2 null points. And it's a beautiful formula. Again, it should be in every algebraic geometry textbook, somewhere in chapter 1. Of course, there is a dual theorem. We'll call it the meet of null lines theorem, telling us that the point A, which lies on the 2 null lines phi 1 equals E of T1 to U1, and phi 2 equals E of T2 U2, is this point right here. Exactly the same expression, except there's square brackets instead of round brackets. So here's 2 examples. Here is our null circle, and here are 2 null points. And perhaps we'll start drawing null points as little white circles to distinguish them from ordinary points, which are usually in red. All right, null points are special, so we're going to treat them specially. So the null points are E3 to 2 and E1 to 3. And what are these points? Well, how do you find E3 to 2? Well, it's 2 squared minus 3 squared. That's minus 5, the first coordinate. Then 2 times 3 times 2, that's 12. And 2 squared plus 3 squared is 13. How about E1 to 3? Well, 3 squared minus 1 is 8. And then twice the product is 6. And then 3 squared plus 1 squared is 10. So it's 8 to 6 to 10. And I've just divided by a common factor of 2 to get 4 to 3 to 5. This is the point that would usually in x and y coordinates be minus 5/13 and 12/13. And this is the point we would usually call 4/5, 3/5. And we want to find that line L that passes through them. Well, there's the expression right there. So remember, that's T and that's U. So what do we have to do? We have to take U1 times U2, 2 times 3, minus 3 times 1. 6 minus 3. And then we have to take T1 times U2. So that T1 times U2 plus that T2 times U1. So 9 plus 2. And third component, U1 times U2, 6 plus T1 times T2, which is 3. That's the proportion 3 to 11 to 9, representing the line 3x plus 11y equals 9. That's the equation of that line. And here's an example with null lines. We'll also denote null lines a little bit differently. Let's, most of the time, try to denote null lines with dashes. Okay, so there's one null line, the dual of our special point. It used to be special, no longer special, minus 1, 0. And the dual of this point here. So E of 1, 0, well, that's minus 1 to 0 to 1. That's the line x equals minus 1. And here's the point minus 3 to 4. It's in triple, it's 4 squared minus 3 squared, 16 minus 9, that's 7, to minus twice the product, minus 24, to 4 squared plus 3 squared, 25. There it is there, the point. There's the corresponding tangent line. So what we're trying to do now is find the meet of these two lines. The meet, that point down there. Well, it's exactly this theorem right here. So there's T1, U1, there's T2 and U2. So we're doing the same thing as we did before. U1 times U2, that's 0, minus T1 times T2, that's plus 3. Then T1 times U2 plus T2 times U1, so 4 plus 0. And then U1 times U2, which is 0, plus T1 times T2, that's minus 3. And we prefer generally to keep the third coordinate positive, sort of a way of giving us a more canonical expression. So let's agree that more or less we'll try to arrange that third coordinate being positive, multiply by minus 1 if necessary. And that's what we've done here to change it to minus 3 to minus 4 to 3. And as a point in ordinary xy space, we would divide by this 3 to give us minus 1 and minus 4 thirds. Minus 1, minus 4 thirds. So you're now in a position to do some reasonably interesting investigations and to also make some computations to solidify your understanding. So to give you a framework for doing that, let's introduce our second standard triangle number 2. This is what we're going to call a triply nil triangle. That's just going to mean that all 3 points are null points. There they are there, alpha 1, alpha 2, and alpha 3. And we're going to choose these particular ones. So alpha 1 is E of 1 to 0. That's the point minus 1, 0, 1. That used to be our special point, no longer special. Alpha 2, which is E of 1 to 2, that's 3 to 4 to 5, up there. And alpha 3, which is E of minus 4 to 3, which is minus 7 to minus 24 to 25, right there. So I remind you, to get something like this, we would take 3 squared minus 4 squared. That's the first entry. Second entry is twice the product, minus 24. And the third entry is this squared plus this squared, 25. Okay, so with this as our starting triangle, we would like to compute lots of things. Well, we'd like to compute pretty well all the things that we computed for our first standard triangle in our last lecture. So we want to compute altitudes, and we want to draw them. We want to compute the orthocenter, the orthic axis, the orthic triangle, the orthostar, the base center, and anything else that you can think of. So let's try to compute these various things. Second exercise, show that the altitudes of this triangle, alpha 1, alpha 2, alpha 3, and the altitudes of its orthic triangle coincide. And exercise 3, somewhat more open-ended, try to generalize any discoveries that you make when you're doing these exercises. You might discover some interesting phenomena here. See if you can generalize that. So, to make this a little bit more fun, let's have a little bit of a competition or some incentive. So, if you calculate some of these things, Please post your answers on the comments for this video. Just for this video, comment, tell us what the orthostar is or the orthic axis is in coordinates, making it very clear and explicit what points you've determined. So fame and fortune await the first to make the calculations. Next time we are going to carry on with null points and null lines. We're now in a position we've really understood what these null points and null lines are and formulas for working with them. Now we can go back to Apollonius's theory of duality. And we can go back to that famous theorem that we started our entire discussion with, namely the idea that the polar of a point is really well defined. We can prove that now. And that's what we're going to do. We're going to have some more interesting formulas next time when we're going to prove results going back to the ancient Greeks. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.